Today's lecture is going to be on determining the noon-sun angle. We're going to use this funky figure 8 Analemma chart to describe how we go about finding it at a different latitude on Earth at a different date throughout the calendar year. Essentially, we're looking at this. How do we calculate how high the sun is in its highest point, or its zenith, on different dates from different locations? So we'll start off and look at a reference of our local area before we move into identifying how to find it at different locations. Let's consider 40 degree north latitude. That's close to our area in the Chicagoland area, but it's technically 2 degrees south of us. But let's work with 40 degrees north. Here's what this graphic is showing. That on June 21st, our summer solstice, the sun travels through the greatest part of the sky. In other words, it has the greatest arc throughout the day. And we would say that the transit is the greatest amount and the sun reaches its highest point. From the summer solstice, as we move towards winter, we reach another date that we would call the fall or the autumnal equinox. In the equinox, you'll find that the arc, the path of the transit of which it takes each day, we get less daylight hours. The sun reaches a lower point in the sky, or a lower zenith, and therefore this noon sun angle would simply be lower. And then a few months after the fall or the autumnal equinox, we reach the winter solstice on December 21st. And notice how low the sun angle is. We would be receiving very low amounts of insolation or incoming solar radiation. The sun is at a low angle, and it rises and sets at a position to where we're getting the least amount of daylight hours. And so then the cycle repeats. After the winter solstice, it begins rising a little bit higher each day. We reach our spring equinox, and then we move back into our summer solstice. So we're observing the angle and the arc of the sun and how they change. This is based on the Earth's axial tilt and relative position to the sun during Earth's orbit. So how do we calculate the noon sun angle? So what is it? Well, it's essentially describing like what point in the sky, how high above the horizon would we find it? So we can calculate this. We need to know that the noon sun angle is going to be a quantification of taking 90 degrees minus the latitude that's given plus or minus the declination. So for example, let's consider the Tropic of Capricorn, 23.5 degrees south. On the northern hemisphere's winter solstice, the sun is directly above the Tropic of Capricorn. We would say that the sun is 90 degrees above the horizon. However, from a greater latitude farther away, the sun's going to be at a very low angle, and we can calculate this. So let's do an example problem, and we'll be referencing this graphic right here. And on the next slide, I've got it a little larger so you'll be able to see it. So let's do a practice run. So what is the noon sun angle, which I'll abbreviate as an acronym NSA, for a city at 40 degrees north on January 28th using the Analemma chart? So first off, we're going to set this up as your noon sun angle is going to equal 90 degrees minus. Okay, so now let's fill in what we know. We know the latitude of what we're looking at. We're looking at 40 degrees north. So minus 40 degrees. Now we need to determine something. We need to set up and solve for the known latitude of the declination. So therefore the declination on January 28th is what we have to find. So we're looking at how do we get this 18 here. And I want you to see that using this Analemma chart, let's find the date that's provided. And I mentioned the date here is January 28th, as identified right here. January 28th. So where is the sun referencing from 40 degrees north? So on January 28th, you'll find that if you use this, and you can't necessarily see it on this video here, but on your handout you'll be able to see it. January 28th is located right here at this date. If I follow it over to my y-axis, I find it's 18 degrees. So now I need to follow the rules. I've got this plus 18. You might say, well, why am I adding this here? Well, if I treat this as if I'm referencing a northern hemisphere, and I know the sun is located above over the southern hemisphere, they're on opposite hemispheres. And because they're on opposite hemispheres, I add them together. Add if they are on the opposite hemisphere. So if the sun were on the same hemisphere, you would subtract it. You subtract if the sun is on the same hemisphere as the date in which you're looking to find the sun. But the sun is located over the southern hemisphere, and we're locating it referencing 40 degrees north latitude. So from the northern hemisphere, the sun's going to be at a low angle. Well, what angle is that? Well, the noon sun angle is going to be 90 degrees minus 40 plus 18. 40 plus 18 is 58. 90 minus 58 is 32 degrees. We would simply describe that as the noon sun angle at 40 degrees north on January 28th the noon-sun angle is going to be 32 degrees above the horizon. That's at its highest point, or its zenith. So we'll get some practice with this. So let's do a practice problem using the Analemma chart with a different scenario. So I'll give you a couple practice problems to work with. So seasonal changes in insolation occur at different latitudes. At any given time, the intensity of sunlight, incoming sunlight, is at a maximum at the latitude where the noon-sun angle is 90 degrees overhead. The latitude of maximum intensity of insolation shifts in the northern hemisphere within the seasons between 23.5, that's on our summer solstice, and the minimum intensity in the winter solstice. Realize that the top of this picture is identifying June 21st. That's our summer solstice. That's when the northern hemisphere is receiving the most direct sunlight. And here we see the winter solstice, December 21st. So the Analemma chart is really showing that. So let's calculate the two practice problems. So what is the zenith of 20 degrees north? So we're talking about 20 degrees north, northern hemisphere, on March 10th. So on March 10th, so now I use my Analemma chart. So I'm going to set this up. I need to find March. March is over here. March 10th is right here. I find March 10th, I take it over, and you'll find that March 10th has a declination of 5 degrees. So using my equation here, noon-sun angle, or the zenith, the highest point, is going to be 90 degrees minus the latitude, which is 20 degrees. They're on the, in this case here, they're on opposite hemispheres, so you're going to add them together, right? The reference point is 20 degrees north. The sun is over the southern hemisphere, so I add them together. 20 plus 5 is 25. 90 minus 25 is 65 degrees. So the zenith at this location, 20 degrees north, on this date is 65 degrees above the horizon. Let's do another one. So what is the zenith on 30 degrees, at the location of 30 degrees south? So notice I'm referencing a latitude that's south of the equator on April 14th. Observe that April 14th is located on the opposite hemisphere. So you're going to add these measures together. So I find my declination here, take this over, it's going to be 8 degrees. So now I can plug in my information. The noon-sun angle, or the zenith, is going to be 90 degrees minus the latitude of 30 degrees. I'm going to add, because they're on opposite hemispheres, add if they're on opposite hemispheres. The reference that we're located, location to southern hemisphere, the sun's over the northern hemisphere. I add them together. 30 plus 8 is 38. 90 minus 38 is 52 degrees. The zenith of the sun, or its highest point, is located 52 degrees above the horizon from a location of 30 degrees south on April 14th of the date. So let's try two more practice problems. I mix it up on you. I will put them on the same hemisphere. So we're going to subtract. So back to the noon-sun angle. So what is the zenith? 25 degrees north. Notice I'm referencing northern hemisphere as my location, and I'm finding the sun angle on the date of August 20th. So I need to go to August 20th. August 20th is going to be up here. August 20 right here. I follow it over, and I have in this case, a declination of 13 degrees. So I have my information. I have my latitude, and I have my declination. So I put it all together. The zenith of the highest point of the sun is going to be 90 minus 25, that's my latitude, minus the declination of 13. 25 minus 13 is 12. 90 minus 12, the sun's going to be 78 degrees above the horizon. It's going to be pretty high in the sky. They're on the same hemisphere as the sun. And my second problem. What is the zenith of 33 degrees south on February 5th? So let's find February 5th. It's going to be over here. It's going to be right here. I find my declination. I bring this over. Right, where did I go? February 5th is right here. And I move this over, I find that it's a declination of, there it is, 16 degrees. It's hard to do on this. It's really hard to look at. So in this case here, I have my information. I know my declination, and I know my latitude. So let's plug it in. The noon-sun angle, which we can call the zenith, is 90 degrees minus my latitude of 33 degrees. My location is in the southern hemisphere. The sun is over the southern hemisphere. So I subtract them because they're on the same hemisphere as one another. 33 minus 16 is 17. 90 minus 17 is 73 degrees. So a question I want you to think about is, so why does the Analemma chart look like a figure 8? Right? Why does it take on this characteristic figure 8 pattern? And the answer is quite logical. It should make sense to you. If the Earth's orbit around the sun was a perfect circle, if it had an eccentricity value of 0, meaning it was perfect circle. If we didn't have these differences, the perihelion and aphelion, then the sun would appear at the same position in the sky at the same time of day throughout the year. The Analemma curve would be but a single dot. But if the sun's orbital path was circular, its axial tilt would generate a symmetrical figure 8, which would be the same size in the northern and southern hemispheres. But the Earth's path is elliptical. The Earth travels at a greater speed at perihelion when it's closer, and it travels slower when it's further. So this effect flattens out the bottom half of the curve on the graph. However, the Earth orbits the sun in an elliptical path and has an axial tilt of 23.5 degrees. Together, the sun's position changes with respect to Kepler's laws, which we'll learn that later, as we view the sun's zenith in the sky. In other words, we're viewing the sun from a tilted Earth that's moving in an elliptical shape around the sun. So it's going to create this characteristic asymmetrical figure 8 pattern. And this just repeats every year. And this is the result of us viewing the sun from a moving platform. Observe the analemma on Earth. Here's a graphic. It kind of shows you. It's pretty cool. Kind of cool to look at. Just different points that have been plotted. And this is what it actually looks like, the analemma on Mars. It has a little different axial tilt, and it has a different orbital pattern around the sun.